Hello and welcome to the fourth video in this series on how to use Threatray. In this video we will cover detection engineering and hunting by creating YARA rules with the help of Threatray. If you haven't seen the previous videos, especially the one on reverse engineering, I recommend doing that first, since it provides lots of information on Threatray that we won't be covering here. As we've introduced in the previous videos, Threatray excels at hunting for code and discovering similar samples, as well as bringing binary intelligence into the disassembler. These capabilities are perfect for creating YARA rules. And during the course of this video, we will be creating two different types of YARA rules. The first one being a detection rule for Latrodectus. The aim here is to create a rule that is reliable enough to be used in production, to alert, to block, and essentially without generating any false positives. The second rule we're creating will be a hunting rule for PlugX. The aim here is to quickly get out a rule that can be used for hunting or used in a non-blocking manner so that we can get more samples or simply to test a rule. We accept that there might be some false positives or false negatives still, but that's okay for a start. This is a rule we could iterate on and improve later on. Alright, so let's get started with the first example on Latrodectus. And in the previous three videos, we used Latrodectus as a malware family to exemplify how to work with Threatray, and we will continue to do so here as well. So first up, to create a rule, we need to have kind of a set of confirmed Latrodectus samples that we can use to craft and also test the rule. And here we will start once again with the earliest confirmed version of Latrodectus originally from Walmart in 2023. And now from here on out, we need to find a couple of similar Latrodectus samples, which of course is something that Threatray excels at. So what we're doing here is we simply navigate to this OSINT Hunt tab, and what we're doing now here is we try to find several similar versions to the one we're currently looking at. And the way to do this is to basically pick a few of these samples that are similar but not equal. So 70%, 40%, 77%, these are all good candidates. So what I'm doing here now is essentially pivoting to each one of those, and I've decided to select 10 similar ones here. I am on one hand recording the hash of these 10 other samples, and I'm downloading these memory regions here which contain Latrodectus, and that will be kind of my basis of my workbench to create the YARA rule. So I have done so for 10 different samples already. I recorded the hashes as well as downloaded the files. And this is what we can see here. So I have these in total 11 files, including the original one that I was just looking at. So I have them ready here in my virtual machine. In two of the previous videos, we've also seen that Latrodectus has some quite characteristic behavioral artifacts. There was this Runung mutex that we could identify as being unique and identifying of Latrodectus, as well as this update file name pattern that also seems to be unique to Latrodectus. So these strings would be actually really nice prime candidates for a string-based YARA rule. However, the OPSEC of this actor is quite high, and these strings are encrypted, and they're only decrypted during execution, so we can't really use them to create a YARA rule. And we can also confirm that here if we run strings on some of them here. We can see there are some strings here to be found, which kind of indicate at least this update pattern, but that is not a common occurrence here. So another version of Latrodectus here doesn't really have any good strings to be used. That also means we kind of need to resolve to trying to find some byte sequences or code sequences between these samples to be able to craft a YARA rule based on that. And of course, that's something Threatray excels at. Threatray is really good at identifying shared code, which we can then use to turn that into a YARA rule. All right, so let's start with our first Walmart sample that I've opened here. And what we have seen in the previous video is that Latrodectus has two distinct variations of string decryption algorithm. We identified this algorithm in the two variations in the previous video. So these two variations are actually a part of what we want to craft our YARA rule on, but they should not be the only part. Given that this part has already changed in Latrodectus after a few months, we cannot really rely that this particular piece of code will remain stable. So what we want to do on top of that is to find a couple of other functions or functionality that we can use as part of the YARA rule in the hopes or expectations that these pieces of code are not going to change a lot, or at least only partially change in the future. And that of course leads us to needing to know which code between those samples is shared and which code is unique, so we can kind of narrow down and pinpoint which functionalities we want to cover with our YARA rule. And the best way to do this is, of course, here with the YARA plugin for Threatray, is to just cluster them, right? So I'm clustering the file I have open here from Walmart against the 10 other files that I have collected previously. And that then gives us this cluster analysis here, which indicates which functions in this set of 11 samples are highly prevalent, as we call it. So here there's a couple of functions that we have in this list which appear in all of these samples. So that of course already helps us quite a lot to narrow down what could be potentially interesting functions. So what I'm actually trying to do here is to find functions that adhere to 3 crucial properties that are suitable for detection engineering. One property is what we're just looking at here now, is that they appear in all of the variations that I'm looking at. The second one, the function needs to be unique to a particular malware family, so Latrodectus in this case. This is something we can verify with retro hunting. And the third property it needs to adhere to is we need to be able to find some sequences of code or bytes that would be unique enough to make sense as part of a YARA rule and not generic in a way that they might appear in other malware families. So a bad example of such a function is the one here, which is called calc_length. Before doing this video, I also spent some time reverse engineering Latrodectus, so some of these functions were renamed during that. It's not necessary to do that. However, in this case, since I want to create a detection rule, I wanted to understand first a little bit what pieces of code could be not only interesting as part of these 3 properties, but also some stable functionality as part of Latrodectus that hopefully in the future doesn't change or doesn't change much. So going back to this calc_length function, which calculates the length of a string, this function is shared over those 10 or 11 samples that we see here. However, if we look at that, we can see that's quite a generic implementation of calculating a length, and it's unlikely that sequences of code in here are going to be unique to Latrodectus. So this is not a function I would be choosing here. However, one function that adheres to these properties is this function here, which is about formatting the bot ID of Latrodectus. Again, appears in all of these 11 similar samples. And if we look at that function here, we can see that we have some nice characteristic sequence of instructions down here, multiplications, RORs, and so on. So that gives us 2 properties. And the third one is to figure out whether or not this function is really unique to Latrodectus and isn't shared with some other families. That is something I can verify with function retro hunting here. So I'm just hunting for this particular function over the 100 million plus binaries. And that then gives us this list of samples where this function appears in. And if we scroll through that list, we can see here on the right-hand side, this function only appears in samples that are also identified as Latrodectus. So this leads us to the conclusion that this function adheres to these 3 properties. So we can find some relevant code sequences. We have established that it appears in all 11 samples, and we have established that it only appears in Latrodectus. So this would then be our kind of input for a YARA rule, and creating a YARA rule based on code can be done in many different ways. The way I'm using here is another IDEA plugin, which is called MKYARA. MKYARA can kind of wildcard all bytes that are subject to change in a piece of code. So these would be memory addresses or offsets. So we can actually take a piece of code here and transform it into a YARA rule that is suitable. So for that, I'm just selecting this piece of code here. I'm skipping over the prologue in the beginning. That maybe is something that changes, but the meat of the function is here. I have MKYARA here, and I can create a YARA rule based on that. And it will give me this little pop-up window here that generates the YARA rule. And we can see here, it's basically just this chunk of a function with the wildcarding applied. So that's basically our start of the rule. And before creating this video, I also went through a couple of other functions that are highly prevalent and essentially went through exactly the same workflow as I've now shown here for this format bot ID. And I've identified 3 more functions around how APIs are resolved, around aspects of RC4 encryption, as well as base64 encoding, which all kind of hold these 3 properties that I mentioned beforehand. And I added them again with MKYARA to YARA rule. And that then looks like this. So the YARA rule here is based on these 4 particular functions that adhere to these properties: the resolve API, RC4 aspects, base64 aspects, and the format bot ID. And if we look at that, that's just a chunk of this function, which has been transformed by MKYARA. What I have done as well is for the 2 decryption variants from the sample from Walmart, as well as a second variant, I have done exactly the same with MKYARA. In the previous video, we already identified what these functions are, so I'm not going to go into details here again, but these are actually string decryption functions which have changed. And they flow into this rule here as well. So if we look at that, that's just another block of code, basically. And then down here I have my condition, must be a PE file. And then we have either one or the other string decryption function. And lastly, we have 3 of those 4 functions that we mandate this rule needs to have. I could do 4 out of 4. It doesn't matter so much. In this case, I want to be a little bit more flexible. Hence, I've chosen to only require 3 out of these 4 functions. Now, with this rule, we can test that on the set of samples that we have collected here. So these are the 11 samples, and we have our rule here, right? That is the rule. So running that over these 11 samples gives me 11 matches. And we're also printing here where it matches. So I have this first Latrodectus, it's matching this decrypt routine, then 1, 2, 3, 4 of the functions we collected. So basically matches 4 out of the 4 plus one of the decrypt variants. And then this one here, for example, matches the first decrypt variant with 4 of the other functions. So we can also run this as a count here. We can see that all of them match. So the rule we crafted matches on all of the samples that we used to actually develop the rule. That's not very surprising in this case. And as a next step, we also want to test this rule on a larger collection of malware samples, as well later on goodware samples. And again, there are many different ways you can test this rule. The way I have chosen here is I've scripted together a couple of things with Threatray's API to fetch around almost 180 unique Latrodectus payloads from a time span of 9 months from the Threatray platform. I've downloaded them here, and these are actually samples here. We'll do a count. So yeah, almost 180 samples, and I now want to test my rule on this set of samples. So we can do a count on these ones here, and then I can see if I scroll through here, all of these Latrodectus samples actually match my rule. So that already gives me a high level of confidence that I've created a rule which can cover and detect Latrodectus. As a last test, what I also want to do is to validate that this rule doesn't create any false positives on known good files. And VirusTotal does provide a free retro hunting service on a large set of goodware. And this is where I also submitted and launched this rule. So I've already done that, so we don't need to wait on that one here. So this is my Latrodectus rule here. Let me just open that. Right, with the decrypt resolve API or C4 base 64 bot ID. It's exactly the same here with 3 out of these 4 functions that I require. And the result here is I'm getting 0 matches on this set of goodware here. So that also indicates that it's unlikely to generate any false positives based on goodware, and hence is now a good detection type rule that I can use in a production setup and start to alert or block based on that. Alright, so in the first video we created a detection rule for Latrodectus and also invested some time to understand the malware family itself, to be able to pick pieces of code that are likely to remain stable over time and that don't cause any false positive detections. With this second example, we want to create a hunting rule for PlugX, and our aim here is to create it quickly without requiring any deeper understanding of PlugX itself. We want to use this rule for hunting purposes only and not for detection. So the example we are starting here with is the same malware attack chain that we explored in the previous videos from Trend Micro report on the APT actor Earth Preda, or also called Mustang Panda. And this actor has quite a high level of OPSEC. And once again, we are not going to be able to create a YARA rule based on some shared strings, but we need to identify some kind of a set of shared code amongst a set of samples here. And what we have open here is this particular sample. I'm not going to go too much into the details of what this sample does. That has been part of previous videos. Just to recap, it's basically doing DLL side loading with Doplugs as the loading component, which then decrypts and executes PlugX in memory, which is this piece of code here. And what we're interested in is creating a hunting rule for just this PlugX implant here. And once again, like in the first example, what we first need to have is a set of similar samples next to the one that we have here. And again, we use our OSINT hunt tab here. That gives me a range of PlugX variants, which were reported from different thread reports. And I'm going through the same iteration here again by locating the payload of PlugX. Again, downloading these, getting the file hash, and I've done so beforehand and collected 6 variants of PlugX. And now I'm jumping over again to my workbench. And these are the, in total, 6 variants, including the one we were just looking at beforehand, that I will be working with. Okay. So the workflow in trying to create a YARA rule for this set of samples is exactly the same as we had with Latrodectus. The, again, only difference is I haven't really reverse engineered PlugX at all. So what I'm doing here is I've opened this initial sample that we looked at that is coming from this thread micro block. I've applied code detections, so you can see annotations here on the left-hand side, what Threatray believes to be code belonging to PlugX. And now next up, I'm going to again cluster this file against the 5 other files that I have selected. That then gives me again a list of functions that are highly prevalent over these 6 samples that I have here. And we can see some of these are also labeled as belonging to PlugX. So that already gives me some pointers what I might be wanting to look at. And again, we try to find functions that adhere to these 3 properties that we established in the beginning. It needs to be shared amongst the samples we're looking at. It needs to be unique, so PlugX only. And we need to be able to find some sequences of code that are kind of characteristic or ideally unique to PlugX in this case. So we have a selection of functions here. We can now pivot or navigate to any of those. There are some functions which might be highly unique to PlugX. However, PlugX is very much obfuscated, so in a lot of functions that you open, you will see these kind of constructs. It's quite hard to figure out what it's doing and if it's doing anything of value. So this is one of these guys. Here's another one. No fun to look at that at all. However, when going through these functions, I was able to identify a few of them which aren't this obfuscated. So for example, this function here is quite compact, is, I would say, characteristic enough. And if we hunt for that, then we will also be able to see that this is a function which is unique to PlugX. So here we have a couple of files where this function appears in, and with a few exceptions here, this is identified as PlugX. So here I'm pretty confident that I can use this piece of code. We can also see that it's not too big, but not too small. So what I'm doing here is again using mkyara to create a rule out of that, which will be one of the functions where I can base my rule upon. I've done so with a couple of other functions. I'm not going to go through all of them, and ultimately ended up at identifying 3 functions which adhere to these properties. And the rule then ultimately looks as follows. This is this one here, where we have a function. This is the one we just looked at. Quite compact. And then 2 more of code that is seemingly unique to PlugX, as well as shared amongst all of these 6 samples. And again, I'm restricting here to PE files, as well as requiring that one of these 3 functions is here. I want to be quite open here and have quite of a broad net I'm throwing out to catch as many possible variants that I can. I could also continue adding a couple more functions here if I can find more, but let's leave it at these 3 functions. And again, let's briefly verify that these are matching here. So this again is the rule we just looked at. Then I have my samples that I used for developing that. And if let's do the count first here. So it matches all 6 of them, which is good. And if we look at where it matches, we can see there is one here with 1, 2, 3 matches. There's another sample with 2, 3 matches. There is one with only 2 matches. Another one with only 2 matches. So we already have some variability in those rules, and only requiring one of these functions to appear in those seems to have been a good choice already. Okay, so similar to what we've done in the previous examples, I first want to quickly verify that I'm not generating any false positives with this rule on goodware data. And if, again, what I've done beforehand is run a retro hunt on the goodware collection in VT with this PlugX rule. So let me open that again. It's exactly the same rule, our 3 functions here with the condition. And we can see over the goodware corpus here, I'm getting 0 matches. What I've done then afterwards is I've run a retro hunt over the last 90 days of VT data, which is this hunt here with the rule, and I got a couple of matches, 6 matches in the last 90 days, even more if you go back further. And now we can inspect those matches here and basically go through these just to briefly inspect. So these might now be a couple more variants of PlugX. So if we look at that, it's a bit unclear, maybe. I've also downloaded all of these, by the way, and analyzed them with Threatray, so we can afterwards go and see what Threatray thinks about them. So this one, maybe PlugX, maybe not so clear. The second one here, also not very conclusive. Third one is even named PlugX, has a good YARA hit here from Modpedia. That is probably PlugX. Then we have one here, has a YARA hit PlugX here from Elastic, so probably also PlugX. And then some here, non-conclusive. Same on this one here. So out of the 6, I would say probably 2 of them are PlugX, given on the intelligence I'm getting here on VT. The other 4 I've downloaded and analyzed with Threatray. And if we look at the results in Threatray, so this is one of those 4, we can see that there is some faint code overlap with PlugX here. However, it seems to be a much smaller sample with only a couple of functions. Might be PlugX, it's an interesting one. The second one here only has very faint overlaps, just a couple of functions, maybe the 3 functions or some of the 3 functions I've selected here, so not so sure that this is PlugX. And then the third one here, we can see we have a clear detection of PlugX, a good amount of overlap here. If we look at the OSINT hunt tab, we can also see similar PlugX variants from OSINT. So this, I would say, is quite a strong signal that this is, we actually found a PlugX variant here. And the fourth one here, we have a suspicious detection with some code overlap with PlugX. Again, looking at OSINT hunt, I can see a couple of other similar samples, again a bit from the same sources, So this could very well also be a PlugX after all. Good, so I think that was quite a successful hunt. We found 6 samples, 3 to 4, maybe even 5 of them could indeed be PlugX. And we were able now to, within minutes basically, to craft a YARA rule for the purpose of hunting, and now have a good collection of new samples to look at. Alright, so that's it for today. With this video you should have gotten some good insights on how to use Threatray to create YARA rules for the purpose of detection engineering and hunting. And thank you very much for watching, and see you in the next one. Bye!